Hello. As promised, in this lecture, I will tell you about a very interesting application of the moment equations for collisionless Boltzmann equation. Okay. So, first of all, let me tell you something about the large stellar systems. So, in general, like when we are doing astrophysics, basically we have to know at least roughly about several stellar systems and their sizes. Okay. So, one is very popular, is called the globular clusters. Now, in these days of internet, you can search over internet and you can have a lot of knowledge about globular clusters. I am just giving you the pathway. Please search. Okay, and if you still don't understand, please let me know, we will discuss. Okay, so one is globular clusters, which contain roughly 10 to the power 5 stars. Okay, roughly. And another is very interesting, which is called the galaxy. Galaxy we all know, and it contains a high number of stars, which is 10 to the power of the order of 10 to the power 11. Okay, and now it's a, of course, in the scope of this course, I will not go into much details of that, but just as a thumb rule, I should say that large stellar systems have larger collisional relaxation time. And what collisional relaxation time is, so that is also something you can search, but roughly saying, if you have some system which has, let's say, tau as the collisional relaxation time, then anything which is happening inside the system, within this time tau, will not have any effect of the collision. So if the tau or the collisional relaxation time is very very large, then for a reasonable time interval, okay, if we study some phenomena during a reasonable time interval, let's say t, which is less than tau, we can simply say that no clear effect or no prominent effect of collision is visible. Okay, and for that case we say the system is collisionless. Okay, and that's exactly the case for this galactic systems. Okay, so the galaxy, for example, a spiral galaxy with this 10 to the power 11 number of stars, some crude approximations, okay, I mean crude but somehow okay, trustworthy approximations give that the collisional relaxation time is much greater than even the age of the universe. So something which has already has, have taken place. Of course, for those systems we can say that collisional effects are negligible. So for these systems we can somehow apply the collisionless Boltzmann equation. Okay. Now, it is true that the Boltzmann equation, when we said that we started applying that for microscopic systems, right? But when it is true that when we are talking of the stars, then the question is, can we apply that? Well, if the total system is much larger with respect to the individual stars or individual components or constituents, basically here stars are the constituents, then why not? They can be thought as the molecule of that large system. Okay, that's exactly the case for both the clusters and the galaxies. The only thing is that the globular clusters, they are having relatively small number of stars, so their tau or the collisional relaxation time is much smaller. So some phenomena, okay, for example the galactic dynamics, okay, some phenomena, uh, I mean they are happening during such a time scale which is of the order or even greater than that collisional relaxation time, and that's why the collisional effects cannot be neglected. Okay, but a priori there is no, I mean, restriction to apply Boltzmann equation for a stellar system. The only thing is that in, I mean, when you can, so both collisional and collisionless Boltzmann equations can be applied in principle, but the thing we have to keep in mind is that when we will try to apply collisional Boltzmann equation, then of course we have to know we have to properly model the collision integral, starting from our knowledge of the nature of interaction. And if the interactions are not very simple like binary elastic collision, instantaneous collisions, then it is a very hard task. And for the stars, this is the case where we have long range and non-instantaneous, actually all the time the gravitational interactions they are working, which is of long range. So that's why, whereas for collisionless stellar systems, collisionless Boltzmann equations can immediately be applied to derive the corresponding moment equations. In principle, the collisional Boltzmann equation can be applied to collisional, how to say, stellar systems, but the, I mean, how to say, the evaluation of the collisional integral to, I mean, to derive an analytical expression for the collision integral and to check which things are conserved in that collision and this type of thing. Okay, and from that finally you, I mean, deriving the corresponding moment equation in order to get rid of that collision integral is not an easy task. Okay, however, there are very good books, okay, of galactic dynamics. You can search over internet and you can just read about that in depth. Okay, you can also go through, for introductory discussion, go through the books which I mentioned in the reference books, okay, in the course handout. Now coming back to this, so this is a typical picture of a globular cluster. This is a picture of a spiral galaxy. Okay, so the collisionless Boltzmann equations plus the moment equations can be applicable to spiral galaxies. Okay, that's true. However, for collisional systems, okay, implementing the collisional Boltzmann equation is not evident, that I just said, due to the long range gravitational interactions. Okay, now Jeans in the year 1922, for the first time he realized, let me do like that, by using the pointer, Jeans in the 1922. So Jeans is the famous astrophysicist, famous astronomer as well, after whose name we have Jeans instability, Jeans mass, Jeans length, this type of thing. So he, for the first time in the year 1922, he realized that the moment equation can be used for collisionless stellar dynamics and for doing very interesting job. So one of those jobs I will discuss here. Now Wood in the 1932 used the momentum equation to find the average gravitating matter density in the neighborhood of Sun in our galaxy Milky Way. Okay, now in this process, what he, followed, both the matter which is visible and which is not will be counted. Okay, so for example, some matter which is not radiating any light or any electromagnetic radiation, so whether you are using visible telescope, light telescope, visible ray telescope, or X-ray telescope or UV telescope, you cannot detect them. Okay, but it's true that when we estimate the matter density in general by calculating the luminosity, okay, we cannot detect them. But he proposed a method by which that can also be detected. So in fact, the motion of the visible stars are analyzed by their momentum equation. Okay, so we can see easily the visible stars and we can study their momentum equation. There is no problem. And the forcing term is due to the gravity field of visible plus invisible matter. And that is the smart point. Try to understand what it is said over here. That is, although we are seeing the dynamics of the visible stars, but what is the forcing? Remember, there is a forcing term A, angular bracketed A, and I said this is the body force other than the pressure term. Okay, there was a forcing term, and I said that is the body force, and usually this is the gravitational force. And the gravitational force comes due to all the matters, whether this is radiating or not. So you understand? So we are studying the dynamics of visible matters, but the visible matters, they are forced due to all type of matters, visible plus invisible. So to do the analysis formally, then we think of a cylindrical symmetry and we take the z-axis to be perpendicular to the plane of the galaxy, which is the R5 plane for us. So we simply say, for example, so that was the Jeans prescription. If this is the spiral galaxy, then we say this is the plane of the galaxy and this is the R5 plane. So this is R, this is the phi, and this is the direction z, which is perpendicular to the plane of the galaxy. And we also use following genes to other assumptions, which is statistical stationarity. That means del del t of any average quantity is 0 and del del z is very much greater than del del r and del del theta. Okay, phi or theta, whatever I mean. Yeah, that is the cylindrical angle, only one. So this is r theta z, whatever. Okay. So basically, the only derivation, special partial derivative survives is the del del z. So if you now go to the momentum equation, which I talked, I mean a number of slides earlier, this equation, this one, okay, then you can just extract its z component and you will simply see this is nothing but 1 by n ddz or del del z here is the same because only along z some variations are occurring, all the other variations are neglected in space. Okay, n times angular bracketed uz square is equal to gz, and gz is nothing but the z component of gravitational acceleration. Okay, this is the corresponding force. Now Wood basically used this above equation for a specific type of stars, K giant stars, which are very bright and easily visible. Okay, he had also another reason for that, because at that time when he did this experiment, the astronomers had some good data for the z profile of the density and the uz of those K giant stars. Once again, go to internet and search what they are, K giant stars. Okay, actually we'll see they are the stars which can be seen from very far in the galactic plane. Okay, now evidently, although we are only concentrating on the dynamics of the K giant stars, basically the forcing which the K giant stars, uh, which is just a small population maybe of the whole mass, the forcing which they are experiencing, that is due to the whole matter density. That is that we call the gravitating matter. That means the matter which is responsible for generating the gravitational force. Okay, so we will classify two type of matter. One is visible matter, one is gravitating matter. So gravitating matter includes visible as well as the invisible matter. Okay. So finally, you will see that from Poisson's equation for gravity, which I expect that all of you know, okay, that is nothing but in vectorial form. Once again, I can write it. C equal to minus 4 pi g rho, and this is the rho of the total mass which is responsible for creating the gravitational field, is given by this. And here for our case, this is equal to divergence of g is nothing but dg dz. So this is, so minus 4 pi g rho gravitational is equal to dgz dz is equal to ddz of gz, and gz is nothing but this one. So we write everything. We know the z dependence of n from our data. I mean, they do it by calibration. And we also know uz as a function of z from our data, and from that Wood did this. Okay, nowadays we have much more sophisticated data of that, but at that time, even for k giant stars, they had very good data, and they calculated using this equation. Finally, they calculated that the rho gravitational is roughly 10 times 10 to the power minus 24 gram per centimeter cube. It's a very small mass, so it's a very dilute matter density. Okay, you try to understand. But when one calculates the matter density from only k giant star luminosity, okay, another homework for you. Okay, because all the assignments are consisting of only MCQ questions, there is not much interesting calculations or much innovative things to ask. So this is my personal request to you, that the things which I ask you to search for during the lectures, please do that. Okay, that's for your thing. That's how you can really learn astrophysics. Okay, so this is actually astronomy and astrophysics both, that how using the luminosity you can infer or conclude about the size of a planet, of a stellar system, or not planet actually, or the star. Okay, star, about the mass of a star. All these things are very interesting. Okay, please learn about that. Okay, now if you do that, then the visible density comes out to be 4 times 10 to the power minus 24 gram per centimeter cube. Now you can tell, sir, these both things are of the same order, and even we don't know that whether they were calculated, there were calculation mistake or not. No, actually it is true that they are very both of them are very small, but actually you see that the one is the half of the other. So this one is the half of the other, and 10 to the power minus 24 is not the matter. So this is actually for both, it's okay. And at this scale, by that time Wood did the experiment, the data were so precise that this discrepancy was something which sought proper physics to be explained. Okay, now you see this discrepancy, rho gravitational minus rho visible, basically is an approximate but very close measure of the invisible matter in the neighborhood of sun. And this invisible matter, in common parlance of astrophysics, we call that interstellar matter. That means, mostly the visible matter, they are the stars themselves, because they are radiating. But between two stellar bodies, what is there? That we cannot see. And that's why we say that they are interstellar matter. Of course, the interstellar matters can also be stellar bodies. Okay, but because they are not detected stellar bodies, we are just calling them interstellar matter. Okay, and this, by this way you can see that we have some approximated measure of the approximate amount of the invisible or interstellar matter. Now it is true that here it is very, the discrepancy of the same order, but the discrepancy can actually be much larger in case of very big galaxies. Okay, and when we are talking about the cosmological scales, okay, and then basically people are talking about the famous problem of dark matter. Okay, now another point is that, so by this way, when you calculated rho gravitational by this way, actually you are somehow calculating, or would calculated the upper limit which is possible, the upper possible limit, okay, for the gravitating mass. So if someone can come out and says that I have another method by which I found that I have 100 times 10 to the power minus 24 gram per centimeter cube, centimeter minus, it's minus 3, okay, is the gravity, is the matter density by some other way. This is not possible, because this is only possible if that type of thing is not a normal gravitating thing. And so basically when we are talking about matter, the matter must have gravitational power. That is something very important. So yeah, whenever if you just learn about dark matter, you will see that dark matters, they cannot interact electromagnetically, but gravitationally they are interacting. So that is the only way they are interacting. So only how you understand gravity, that there are dark matters, only by their gravitation, so their contribution to the production of the gravity field. Okay, so you see, this value is the, the higher value of the matter, which can include dark matter as well. Okay, so visible plus, I would not call at this moment dark matter, but just visible and invisible matter. Okay, and this is known as the upper limit of interstellar matter, or the famous Wood limit. Okay, so this is called Wood limit. Sorry. Okay, so mm, yeah. So in the year of 1932, this was, to be very honest, the formal astrophysics was not that developed. Well, it was developed somehow, but not that much developed. In the year 1932, they did not have very much sophisticated observational tool and instruments, but you see that Wood came out with a revolutionary idea, just using what? Collisionless moment equations. Okay. So from the next lecture, that was one of the very interesting applications of the moment equations of a collisionless system. Now, from the next lecture, we will again concentrate on the moment equations of a collisional system, and starting from its equilibrium distribution, okay, which is nothing but the Maxwell-Boltzmann distribution. We will show that we finally can derive some, try to derive, or actually will be succeeding to derive a dynamical theory, okay, and which will be the theory of an ideal fluid, okay, or equation of an ideal fluid. Okay, thank you very much.